Thank you. This is Kapsabet post-mock examination, physics paper 1, the year of 2025. You are highly welcomed to this live session, whereby I request that you subscribe, you share, and you also ensure that you have consistency in following us on YouTube. This is Ascending Trades. Welcome, and feel that you are in the right platform for academic journey and progress. Then you are told question 14, section B, say two conditions necessary for a system of force acting on a body to be in equilibrium. We know that this is all about equilibrium, an issue of balance. So we need to look at the issue of a body having a balance. So, number one, we have the principle of moments. The sum of clockwise moments must be equal to the sum in the clockwise moments. Then we'll be getting our point 2. That is 1. Then our point 2 is that the upward forces must be equal to the downward forces. You have an application question, 14B. 14B. The figure below shows a loaded wheelbarrow held in equilibrium by a gardener. The wheel of the wheelbarrow is in contact with the ground at point C. So you can see clearly where we are having our point C. Then you are told there are 3 vertical forces acting on the wheelbarrow. We have P, this one, acting upward. It is applied by the gardener. We have Q, is the upward force of the ground on the wheel at point C. This one. We have W, is the weight of the wheelbarrow and its contents. Explain why the force P is less than the force W. So you can see we are having our Q here. This is our W acting at the center. We have the wheelbarrow is in contact with the ground at point C. Then you are told, explain why P is less than force W, considering, in this case, we are going to consider the P itself, the Q, and the W. So, if you look at the wheelbarrow and its contents, when they are in equilibrium, considering the wheelbarrow, plus the contents. So in what we call in static equilibrium in vertical direction. Then the upward forces equal the upward forces. So we can mention the upward forces in this case, where we have P, Q, and W. They have upward forces. In this case are P and the Q, which is the reaction, whereas the downward force is W. So this is just an explanation. What does this one tell us? It means that the upward forces, P plus Q, then we get weight. And what does this one mean? It means that our P will be the same as Q minus, sorry, it is supposed to be our W. Supposed to be our W minus Q. And that is why you can say that P is less than W. P is less than W in this case. P is less than W in that case. So when we are going to use the moments of forces P, W about 0.0. So our 0.0 will be our pivot, or we shall be measuring all our distances, our perpendicular distances from point C. So in this case, where we say force 1, D1 is equals to force 2, D2, because we're considering P and P and W, about the same point. So let's compare the distances from the pivot, yeah? The distances from the pivots. So we can look at, for W, this will be the distance. We can call it dW. And then from the same pivot to where we have our point, where we have the action of force P, then you can call this one dP. So if you compare these two distances, you'll find that the dW is less than dP. So when you use the principle of moments, then we can say T a force P times the perpendicular distance dP is equals to force W times dW. So in this case, we know that the dP, the distance, is greater than dW. So if we make the P to be the subject of the formula, then P will be given by W dW over dP. Therefore, this implies to us that directly P is less than W. P is less than W. That's why, because it is having a longer perpendicular distance to balance W, then that automatically gives it the mandate for it to be small or to be less than W. The figure below shows a lorry full of liquids. Study the diagram and answer the questions that follow. You're told the tanker delivers the liquid and drives away empty. So At first, it had some liquid, and then now it becomes empty. Then you are told compare the acceleration of the empty tanker with the acceleration of the full tanker for the same resultant force. Remember, resultant force, now our resultant force, F, we hold this one to be constant for when empty and when full of a liquid. Therefore, we can say our empty tank, to award it a mass of M1, and when it is full, in short, it is with liquid, you can award it a mass M2. So, for those who may not understand fast, let me include this one. This is the tanker alone, and this is the tanker plus oil. Therefore, we know that the resultant force F is always given by MA. So now, let's make this one to have acceleration as the subject of the formula. A is given by F over M. Now, for case 1, we can say that, let me just write here, case 1, we use when it is empty. Then you can say A1 will be given by our force over M1. Case 2, when it is full, our A2 will be given by force over M2. Mathematically, let's compare something here. The moment you are having a denominator that is increased, remember when you are having a denominator and it is increased, then the value of the subject will be reduced. So, if we compare this part and this part, you'll find that the value of A1 is greater than the value of A2. I still think that we need to elaborate further. So A1 is equals to force over M1. And A2 is equals to force over M2. So, since this one has been lowered, we increase this. And this one has been increased, we lower this. That is what the question is trying to ask. So, we can say that the acceleration of an empty tanker is greater than that of a filled tank, a filled tanker. Can I proceed to the next question? Given that an empty tanker has a weight of 50,000 newtons, the forward resultant force, is 6,000 newtons, and the total resistive force is 2,000. Then you are to determine the acceleration of the tanker. So the first thing here we need to get is the mass of the tanker. So mass of the tanker will be given by weight over G. And this one is 50,000 divided by 10. And you are going to get 5,000 kilograms. 5,000 kilograms. The next part that you need to look at is the resultant force. So, a resultant force will be given by the applied force, which is 6,000, minus the resistive force of 2,000. So it will be 6,000 minus 2,000. And you're going to get 4,000 newtons. So now, after you get F as 4,000, then you can say that from force is equals to MA. Then our A will be given by force over M. And this is 4,000 divided by a mass of 5,000. I'm going to land at 0.8 meters per second squared. 0.8 meters per second squared. A warm bottle of soda placed in ice at 0 degrees Celsius cools faster than when the same soda is placed in water at the same latent at the same temperature. Explain these observation. Explain these observation. So the ice is at 0 degrees Celsius. Remember, it will take time. It will keep absorbing heat energy from the bottle for it to melt. Unlike where we need to strain raising the temperature of this water. So in this case, you can say that the ice absorbs latent heat of fusion. It absorbs latent heat of fusion. Latent heat of fusion. We're having a certain figure here. The figure shows an incomplete circuit setup that can be used in an experiment to determine the specific heat capacity of a solid block by electric method. Study the diagram and answer the questions that follow. So this is the diagram. You can see we are having a source of current here. We have thermometer, we have the heater. Kcse. Then you are told, state the purpose of the rheostats in the experiment. State the purpose of the rheostats in the experiment. Rheostats is used to control the amount of current. Rheostats is used to control the amount of current. Regulates or control amount of current. Complete the diagram by inserting the missing components for the experiment. So let's get back to the diagram and see what is supposed to be missing. The first thing that we need to locate here is this electrical method. And we know that energy can be given by VIT. So generally from this one, we should include the measurement of the voltage and the current. We know that voltage is measured across the source like this. So that one is included. We are having a switch. So at this part, we can include the ammeter. And show that we are having our ammeter there to give us the measurement of the current, because it is put or it is connected in series with the circuits. We have something else missing. Let me check. No. Then the next question says, other than temperature, state 3 measurements that should be taken. So in this case, we have, I had given previously energy or work done by electrical device. The heating device will be given by VIT. Therefore, we need to measure all these 3. So we have voltage or potential difference. We have the current, and we have the time taken during heating. The time taken during heating. We have part C of the same question. The figure below shows a setup of operators used in an experiment to determine the specific heat capacity, the specific latent heat. It's supposed to be specific. Okay. Latent heat, it's okay. Or fusion of ice. Study the diagram and answer the question that follow. So we are having the connection in that manner. Then you are told that the mass of the beaker is equivalent to 260 grams. The mass of the beaker plus the melted ice is 280 grams. So from this case, we can get the mass of the ice as 280 minus 260. And we are going to get 20 grams as the mass of the ice. Then the question that follows asks us to determine the energy supplied by the 120 watts heater in 10 minutes. So we know that power, that is energy dissipated, can be given by the power times time taken. So we are having a power of 120 watts. You multiply by the total time of 10 minutes, which is equivalent to 600 seconds. So 10 minutes, you convert them into seconds by multiplying by 60. And this will land us at 72,000 joules. Now you're told the specific latent heat of fusion of the ice. Remember, if you get back to the diagram, you will find that we are only focused on the amount of heat that will be received by the ice only. Because as you can see, we are having this filter funnel, and then it will allow the water to, the melted ice to move away. So the melted ice will not be receiving any further form of heat energy. Therefore, we'll concentrate only with the energy dissipated by the electrical equipment and the energy that will be absorbed only by the ice until it melts. Therefore, we can say that energy dissipated or energy supplied, the heat supplied will be the same as heat gained by ice. Therefore, 72,000 joules will be the same as the mass of the ice times the latent heat of fusion. Therefore, 72,000 will be equivalent to 20 grams, which will be 0.02, I think, 0.02 kg times LF. Maybe somebody will miss what we have done over here. We have the mass of ice will be the same as 20 grams, and this is equivalent to 0.02 kg. So let me convert for those who may catch up slowly. Then times LF. So making our LF, which is the latent heat of fusion, as subject of the formula, we'll get 72,000 divided by 0.02. This one will give us 3.6 times 10 raised to power, that is a positive number, power 6. That will be the latent heat of fusion. That will be the latent heat of fusion. The experiment value for the specific latent heat of fusion of ice obtained is less than the theoretical value. Give a reason for this. Some of the heat energy might have been used. Some of the heat energy may have been lost to the environment. Remember, from the setup, some heat will be lost to the environment. We have our question 16. The figure shows a conveyor belt transporting a package to a raised platform. The belt is driven by a motor. So you can see where we are having a motor. These are conveyor belts. And if you look at the setup, it's like an inclined plane. Then you're told the mass of the package is 36 kg. Determine the increase in gravitational potential energy, GPE, of the package when it is raised through a vertical height of 2.4 meters. Remember, GPE is given by mass times gravity times height. Then this is what we are asked. We have the mass as 36 kg. We have our gravity as 10 newtons per kg, and we are given our height already there. So we substitute 36 times 10 times 2.4. And this one is going to lead us into 864 joules. 864 joules. Then the power needed to raise the package through the vertical heights in 4 seconds. We know that power is given by the work done over time. We showed that is the rate of doing work. And the work done here, we had been given in terms of potential energy. So we can have our GPE divided by T. And this gives us 864 divided by 4 seconds. This will land us onto 216 watts. And 216 watts. Then part C, the electrical power supplied to the motor is much greater than the answer to B. So our previous question, we have got as 216 watts. Then we are told the electrical supply to the motor is much greater than the answer in our B above. Explain how the principle of conservation of energy applies to this system. In this case, the extra energy supply does not go into waste, but it goes into overcoming inefficiencies like friction and losses. Since the energy is supposed to be conserved, then some of this energy goes into overcoming such inefficiencies such as friction and heat losses. Therefore, I can say the extra energy supplied does not go into waste, but it goes into overcoming inefficiencies such as friction and heat losses. Assume that the power available to raise the package is constant. A package of mass greater than 36 kg is raised through the same height. Suggest and explain the effect of the increase in mass on the operation of the conveyor. The moment we increase the mass, then we maintain the power, then it means that we are going to increase the time taken to raise it. And this is because an increase in the mass or the weight of the load will affect the speed by lowering the movement of the belt. So the time taken to raise it increases due to increase in weight or mass of the loads. The velocity or the speed of the belts lowers. So if it is going to move at a lower velocity or speed, then it is going to increase the time taken. An athlete of mass 64 kg is bouncing up and down on a trampoline. At one moment, the athlete is stationary on the stretch surface of the trampoline as shown in the figure. So we are having this one as our figure. Then she is standing on the trampoline. State the form of energy stored due to the stretching of the surface of the trampoline. Remember, stretching materials, they do contain elastic potential energy. They contain elastic potential energy. Stretching materials contain elastic potential energy. So this one is held by stretching materials. We can still have the likes of springs, etc. They contain that energy which is stored in them. The stretch surface of trampoline begins to contract. The athlete is pushed vertically upwards and she accelerates. At time t, when her upwards velocity is 6 meters per second, she loses contact with the surface. Determine her kinetic energy at time t. Remember, kinetic energy is given by half mv squared. And in this case, we have the mass of these athletes, which is 64. And we have been given the velocity in which she is moving at. So half times 64 times 6 squared. And this is giving us, from computation, we get 1152 joules as our kinetic energy. The height at which the kinetic energy will be 0. When the kinetic energy is 0, it means that all its energy has been converted into potential energy. So when Ke is equals to 0, then it's all converted to potential energy, meaning that Ke will be the same as Pe. So our Ke here will be the same as Pe and will be given by mgh, because this is what we want as per our question. Therefore, our kinetic energy of 1152 will be given by a mass of 64 times a gravity of 10 newtons per kg times a height h. Making h the subject of the formula, it will be 1152 divided by 64 times 10. So our height here becomes 1.8 meters. It becomes 1.8 meters. In practice, she travels upwards through a slightly smaller distance than the distance calculated in Roman 2. Suggest why it is so. Remember, from this calculation, we have got 1.8, but our part C is telling us that we should be expecting a smaller distance of less than 1.8 meters. So remember, as this lady athlete moves upwards, she's going to face some air drag. She's going to face some air drag, that is friction of the air. She's also going to have some dissipation from the trampoline. So all these ones may not be counted for, and that may bring the distance or the height to be less. At the trampoline, springs are tested. An extension against load graph is plotted for one spring, and we are given this. Then you are told, on the same axis, sketch a graph of another spring whose spring constant is higher than that of the trampoline. So in this case, since we are having extension against the load, remember, we are all used to force or load against extension. But now here, in this case, we are having a extension against the load. So we know that a graph of force against extension gives us the spring constant direct. But now in this case, the spring constant K will be the same as the inverse of the slope. K is the same as the inverse of the slope. Therefore, if we want a spring of greater or higher spring constants, on the same axis, sketch a graph of another spring whose spring constant is higher. So let's say this is K1. We need to have another graph that is showing that K2 is greater than K1. So in this case here, since K2 is equals to the inverse of the change in slope, and the K1 is also equivalent to the inverse of change in slope, then how are we going to obtain something that is higher? So in this case, for us to get the graph, then we need to have this one having a lower slope so that we can increase the spring constant. If we lower the gradient, then we are going to increase the spring constant. So how is this one going to happen? How is this one going to happen? It is going to happen like this. Suppose we pick one part like this. We pick one part like this. Like that. So we can see we are having the first, we can call this one to be E1. And now we need to have another part as E2. We can call another part to be E2. If we cannot use these methods, we can also go for the method of from K is equals to force over extension. Then our K2 is equals to force over extension. So what will happen to the extension? So that we have a greater K2 being greater than K1. Then we must lower the extension. So now if E1 was for K1, then what can we do so that we get a E2 which is smaller? So allow me pick this one. Like that. So I'll say this is my E2. And at this point, I draw my graph. So it will be like this. And you can call this one as our X2. So that one becomes our graph. So I can say our E2 is less than our E1. our K2 will be greater than K1. And we've closed the business of the same. The diagram below, that is question 18 now. The diagram below shows a setup used to investigate the particles of gas law. Study the diagram and answer the question that follow. Look at the diagram clearly. We're having a pressure gauge. We have our thermometer. We have some water bath. We have dry hair inside this flask. We have a source of heat. State with the reason which gas law is being investigated or experimented by the setup. This one is the pressure law. It is the pressure law or the gay LUSSACS. It is the one that is called the pressure law. It's the one that is called the pressure law. Why do we say it is this one? It says that at constant volume, the pressure of a fixed mass of a gas is directly proportional to its absolute temperature in Kelvin. So we are maintaining the volume of this one. So we can say the volume. The reason is because the volume is maintained. The volume is maintained. So what is going to vary? We have the temperature and we have the pressure. Name two factors that are held constant in the experiment. Number one, we have the volume. And number two, we have the mass of the contents. We have the mass of the contents. Give the reason why heating is done through a water bath. Why heating is done through a water bath. Remember, in this case, we need to ensure some even distribution and not just an abrupt heating, but in heating that is occurring in a gentle manner. So you can say that it ensures a water bath ensures even and gentle heating. And this one preventing local overheating. Preventing local overheating. What do we mean by local overheating? Is when we have one side being overheated than the other one. We are having a certain diagram over here. The figure A shows 52 centimeters of air trapped by a mercury column of 10 centimeters, while in figure B shows the column of air when the glass tube is inverted. So you can see the volume of the right column is increasing from 52 to 60. So it is inverted. Then you are asked, determine the atmospheric pressure in millimeters of mercury. So in this case, we need to look at the pressure of the air. The pressure of the air, of the trapped air in this case, will be as a result of, you can see the mercury column is acting downwards. So we have the mercury column. Remember, we are working with the centimeters. So it will be 10 plus, we have atmospheric pressure, ATM. Then our pressure 2, in this case, it will be the ATM, because it is only ATM that is acting like this. Then it is counteracted by the height rho G, the height of the mercury column. So it will be ATM minus 10, like that. So now, since we want to solve, we can let ATM be X. So my P1 will be the same as 10 plus X, and my P2 will be the same as X minus 10, this one now. So from P1 V1 is equals to P2 V2, then 10 plus X times our volume 1, we are going to pick a column of 52 centimeters times 52 will be the same as P2, which is X minus 10 into a volume of 60. Why are we using the volumes as the height columns of the hair? It is because all these tubes are of the same cross-sectional area. So this one, it becomes 520 plus 52x is equals to 60x minus 600. So now we want to have x as the subject of the formula. So we group the like terms together. So this one becomes, we pick this one to the left side. So it becomes 520 plus 600 is equals to 60x minus 52x. So 8x is equals to a sum of this one becomes 1120. 1120. So our x becomes 1120 divided by 8, and our x becomes 140. 140. And since everywhere here we were working with centimeters, so we expect this one to be 140 centimeters of mercury. But the question is asking us to get it in terms of millimeters of mercury. So our x in millimeters of mercury is supposed to be 1,400. 1,400 millimeters of mercury. You may doubt the question, but that is the reality. It is from the calculation. We all know that the maximum of an atmospheric pressure is supposed to be 760 millimeters of mercury. But now, in this case, because we are just doing some calculation, you just let it be at 1,400 millimeters of mercury. The graph below shows the relationship between the pressure and temperature of a gas of volume 1. On the same axis, sketch another graph of gas of a larger volume. So in this case, we are supposed, the moment we increase the volume, we are supposed to decrease. So from PV is equals to nRT, even though this is not of our level, then we expect that if we make P the formula, is given by nRT over V. So if we increase the volume, then we expect the pressure to be reducing. So if we have our volume 2, which is greater, then we expect the pressure to decrease. So we can have a graph of reduced pressure like this. Now we can proceed to this question. That is part C, Roman, is it supposed to be C or what? Okay. The figure below shows a ball spinning in anti-clockwise direction through still air. So this is the spinning ball. It is moving this direction. The horizontal distance covered by the ball is observed to be longer than the ball when the ball is not spinned. Explain how this increases the range of the ball. This will be a narration, so we can go direct to the narration and see what varies. As the ball spins, there is variation of velocities and pressure. The pressure differences, the pressure produces a lift. The ball, therefore, stays in air longer, stays in air longer. Making hits to move a further horizontal distance when with no speed. When with no speed. The last part, you're told the figure below shows gas flowing along a pipe, non-uniform cross-sectional area, two pipes A and B, dipped in liquid as shown. You can see the cross-sectional area of these parts is larger than the cross-sectional area of these parts. So in this case, we expect variation of the pressure, the velocities of the gas. So if we say we are having the gas traveling at V1 in this one and V2 in this part, then we say that velocity V2 will be greater than V1. And this one at the other way around is going to adjust and provide that if we are having pressure 2 here and this pressure 1, then we shall provide a greater pressure P1. So P1 will be greater than pressure P2. So since we are having a lower pressure here, then the atmospheric pressure will force the liquid to move a greater height column in B. Therefore, we can have that as the level in B, and we slightly draw a lower one in A. So, you can say at B, the gas travels at a higher velocity, creating a low pressure zone. Higher atmospheric pressure forces the liquid up. What can we say? In summary or in short, the pressure above B supposed to be talking of the velocities. The velocity above B is greater than velocity above A. Thank you so much for tuning in to Ascending Degrees, your trusted place of your academic journey. In case of inquiries, you can reach me through 0757 01 9011. During the December holiday, we shall be having a 5 weeks non-stop engagement on sciences and mathematics. You can make the inquiry through the number on your screen. You can inquire as early as now and get enrolled to our classes. Thank you so much.